Welcome. You are about to view a recorded talk from the online seminar series Progress and Visions in the Scientific Study of the Mind-Matter Relation, held in 2018. The seminars aim to bring together researchers from around the globe with a background in mathematics or physics who are interested in the scientific study of consciousness and the mind-matter relation. While each seminar session consists of a talk and a discussion, the latter is not recorded and the following video will only contain the talk. We hope you enjoy it. For further information, please visit mind-matter-relation.org.
Thank you, Jonas and Robin, for setting up this amazing thing. I mean, it seems to be working perfectly well and all that. It's a fantastic format for maybe to go further with other things too. Welcome, everybody. I mean, I wasn't expecting to see really faces on the screen, but it's nice to see that. And to see some of you back after several years, that's also nice. So you see my slides, I assume, right? Okay, so good. So let me start with the talk. So I've put some references here, which are sort of the background material to what I'm going to talk about. But I will try to go well beyond this material in the discussion that we have. So the first thing I mentioned is the book, which was just brought up by Robin. There's a paper of 2010, which was my start into natural language work. And then more recently, there is this paper on conceptual space, 2017, which was my start into cognition. So I never really did much in these areas before. What do I have to do? Oh, you have to switch screens. Okay, good. So I'm going to start with the sort of quantum background to my talk today, because it's supposed to be on the interface of physics and cognition. And in this case, in my case, will be quantum structure and cognition, although I will qualify later what I mean by this connection. And so what I'm going to do is that I'm mainly going to follow for a little bit what we did in this book, and then we're suddenly going to deviate from physics to other areas. Okay, so process theories and quantum. Here's the picture. If you haven't bought it already, you should do so. It's quite big. Yeah, anyway, there you go. So that's the book. We spent 3 years writing it. And then we start with pictures like this. So basically what we're talking about there is the idea of physical processes as boxes and systems as wires. So here you see an example of a physical process which takes some system in and some systems out, which are photons. But this is, of course, not the only thing which can be described in such a way. Here's a computer program which takes lists in and produces lists, preferably ordered. And we can use the same language for that. Or we can take this, well, this is actually the full book of English cuisine. So, which takes 2 systems in and produces 1 system. This is another process which, yeah, also takes 2 things in and produces 2 things, right? Right, okay. So now what you want to do, so this is sort of the elements, if you want to talk set theoretically, the elements of the sort of maths we are going to use. These are the elements, but usually in maths you got operations too. So we want to compose things, and if you travel and like everybody, you want to hang up your favorite painting in the hotel you are, then you bring your power drill, and you will need an adapter and plug things together to actually get that hole in the wall and get kicked out of that hotel, because that's what usually happens if you do that. So basically, then you make this composite of these boxes in order to produce something which is then representing the little picture on the right. And that is composition. And in fact, it looks very easy, like you just compose the wires together. But it's really important that these wires sometimes carry labels like EU plug, UK plug, because you can't compose the wrong things with each other. And an important part of the structure what we're dealing with is that you only can compose certain things to other things. Because if you, for example, do this, then this is going to cost you a lot of money. This is going to cost you money, right? Yeah, it's going to cost you money. You don't want to do that. I mean, I'm sure it already happened in reality in many cases, because some of these processes are hard to control. But okay, so right, so this is the composition structure, and then once, okay, so what is the sort of, I mean, I did give you a definition of what such a thing is when it's well composed, and we call this a diagram. And the definition of a diagram is really given by what we consider as equal diagrams. So a diagram is just a bunch of these boxes which are wired together, and two diagrams are equal if they consist of the same boxes and are wired together in the same way. Now, another aspect is that there are designated inputs and outputs. That's another sort of piece which is important to mention to actually identify. Right? So what you see there is a tautology by definition. That's a tautology by definition, and that's the only thing we really will need in this talk to reason about the things we want to reason. So there are some special kind of boxes. We represent them by this sort of triangles and upside triangles and square boxes. We call them states, effects, and numbers. And I mean, here you may recognize Dirac notation. This is exactly the same thing. This is a Dirac notation rotated 90 degrees. If you compose a state with an effect, you can think of that as an inner product, and you produce the Born rule, right? It's really like the bracket thing of Dirac notation, nothing more. Which isn't good, because in such a formalism, you always get some way of doing quantitative evaluation. This could probably give you a probability. And in some of the things I'll talk about, this is kind of important, that you have this sort of generalized Born rule for all theories which follow this sort of formal template. I mean, this is a mathematical formalism, what I present. It's a bit different than set theory. I mean, it's not a bit different than set theory. It's radically different than set theory. Some people who have heard about category theory, I could tell this is in some way, this is category theory. You can justify these pictures algebraically using category theory, but this actually makes it more complicated than necessary. That's something important to say. I'm not going to go into this because this is about mind matter, but it makes it artificially complicated because category theory is still very much built upon set theory, and the set theory is what makes things complicated, really. So this is much simpler here. Anyway, you can, with these diagrams, you can do things which look a little bit like algebra. For example, what you see in this picture is I introduce a tensor symbol to say, okay, we take two diagrams side by side, and this is really what this is a perfect analogy with the use of tensor product for linear maps and Hilbert spaces. This is like the Kronecker product, really, but it just means that you put two pictures side by side, so it's a bit easier to compute. And then you can also sequentially compose two of these things. You have to be a little bit careful, because the input of what you stick at the end of something has to match what you stick it to. So that's why I put these labels A and B there. So you got these two modes of composing processes. And actually, what category theory, if you like, that will do for you, it will axiomatize these two operations for you and the way they interact. And that's then a way of actually saying what these diagrams are. But it turns out to be more complicated than just saying, hey, I've got a diagram. It's simpler, because I didn't really need much effort to define this. Well, the same thing I'm explaining now to you in the category theory textbook you find on page 300, after learning a lot of stuff and doing a few university degrees. So this is simpler, I guess. Okay, so now the only thing, so the reason I gave you this operation is to make it connect to things people may know here. For example, I know Pedro is a category theoretician, very much so he knows these things. But the main reason I actually introduced these two operations is to define something we call a circuit, and it's the name which people use in quantum information for circuit. Some computer scientists may think of something else, but a circuit is a picture or a diagram you build using these two operations, like one which can be thought of as after and one which can be thought of as while. And then you get like things which you see here, which you can break up by just putting cuts horizontally and vertically, and that's what we call a diagram. And one can prove some theorems about a circuit. One can prove some theorems about these circuits. But the most important one is that they are boring. They're not much fun. Okay, if I say circuits are boring, I'm talking about these diagrams means I'm going to talk about something more interesting. And to get motivated to go there, we go to Erwin Schrödinger. And one of the things Erwin Schrödinger said around 1935, which is very interesting to put this in an historical context. I'll first say what he said. Well, he said that the main characteristic of quantum theory is pretty much what's happened when when you put two systems together. A lot of people associate this specific phrase with what's called quantum steering, but I think Schrödinger was probably thinking a bit broader about this. Really, you put two things together and something weird happens. And he says this is the characteristic threat of quantum mechanics. Now, of course, around the same time, you had John von Neumann starting what is called quantum logic. I mean, I'm sure in this talk series there will be people talking about quantum logic because there is some branch of quantum which they call quantum cognition, where they use quantum logic to model concepts in the brain. So you hear people talk about this. But like independently, so von Neumann came up with quantum logic by considering the characteristic threat of quantum mechanics, what happens when you measure a system. So that measurement is not observation, and that you get a logic of propositions, which is not a Boolean logic, so to say. And that had a very big impact, and lots of famous mathematicians and physicists start to work on quantum logic, although in all fairness, it seems to be pretty dead now. And I want in particular to contrast this idea of like looking at a single system, observing it, and see what comes out with looking at multiple systems and not thinking about measurement whatsoever in the first place, but just the idea like, okay, what's the new system? And now think about it. So we want the logic which at its most primal level wants to give you the ability to talk about multiple systems. So the diagrams I've been writing, let me go back to one. Yeah, I can take, so on the picture on the left here, you see two wires side by side. What does that mean? Well, it means we got two systems. It's there. The moment you write two wires side by side, you're talking about two systems without any further ado. This can be anything, but this is literally, so the most simple picture you can have is one wire. Okay, I agree. Second simplest picture, probably two wires side by side. I mean, we're talking about a composite system at that level already. And then you can start doing more complicated things with this system. And what we really want is then say something about the sort of ways we can compose systems, or I don't know, and we hope that will tell us something about, in the case of Schrödinger, quantum theory and what structure it takes. And that's indeed what we are going to do. And we are going to try to say what Schrödinger had in mind here by just saying something about our diagrams. That's the idea. So in a way, this could be called quantum logic take two, if you're prepared to call this logic. And I actually am more prepared to call this logic, especially for reasons of where we are actually going to get in this talk and see how it's connected to other things like language and cognition. That definitely deserves the word logic. You know, in a way, quantum logic got its name by being different from logic and by failing to be a logic, because the deductive principle failed. So, hey, quantum theory is a logic where the deductive principle failed. Okay, cool. So what can we do? I don't know. We can't do logic. I mean, that's kind of what quantum logic was. So here we got something where we actually can do things, and in a way, this is a hyperlogic. If you think about deduction here, I'll explain this later. It's more logic than normal logic. Now, okay, so let's try to articulate Schrödinger's dream, so to say, like what is sort of the most primal structure which gives us some behavior you get from quantum mechanics. And I'm going to define it in two ways. So the way to think about it conceptually first is, of course, we got things like entangled states. It's like a state of two systems which is entangled, and which maybe we can sort of get closer to quantum theory by saying our diagrams or our circuits or whatever have special states, quantum states. I'm saying here circuits because that's how the physicist in the laboratory thinks, and that's how the physicist in the laboratory wires things together. So these are our boring circuits, but we stick some interesting state in there. So maybe can do interesting stuff. And I'm giving some equations here. The two equations on the right, they're just basically symmetry equations. They say if you swap the two systems, like you have to think of these big triangles as a state of two systems, the one with two wires out. And it says if we swap the two wires, we get the same thing. So the state is symmetric in the two systems. That's all it's saying. So that's not deep. The other one is kind of deeper, but you need a little bit of imagination to understand what this other equation says. It says that there is some way to take this state, and then if you think in Dirac notation, the corresponding bra, which is an effect, which is just obtained by flipping the picture upside down, and you configure that in a certain way, you get an identity, a plain wire. Is this weird? Yes, this is really weird, because if you think about classical systems, if you take two classical systems, like two pens or something like that, can people see this if I do this?
Yes.
That doesn't matter. So you take two pens, like I describe two pens by saying, this is a black pen and this is a blue pen, and I'm done. So how would this look in pictures? Actually, in pictures, taking this big triangle on top, it would actually mean that this triangle breaks up in two pieces. One little triangle describing the first, one little triangle describing the second system. They're independent. Because these two pens are totally independent, so you would describe them by two triangles which are disconnected, not like one big triangle. So that's why we use the big triangle symbol to show these two systems are connected in some way. They're entangled. And if you look at this equation there, it's sort of saying, I mean, if you think about it, if you would substitute these big triangles with two small triangles, then the input wire would be totally disconnected from the output wire, right? And there's no way you could get like an identity or a flow of information. So this equation in some way is saying there must be something special going on within these triangles, that whatever goes in gets to the other side. It has to go, so you have to think of time going upwards. So it's sort of, it goes up, then it goes down again, and then it goes up again. Just ignore that. We're in an interesting world here. We're not in the boring world anymore. We're not in the boring world anymore. So something interesting is happening here, something confusing maybe, but it's an interesting equation. So that's one way of, and for people who know a bit of quantum information, they see this quantum teleportation post-selected. That's what it is. Just quantum teleportation post-selected. But it's an equation you find in category theory books too, from the 70s. This is called a compact closed category. So it's something which, it's an equation which doesn't just come from physics. It occurred already in mathematics too. And now to actually really, so you put in this special state. There is a completely equivalent way to define what I'm trying to define here, like adding these special states. And a completely equivalent way, which is a bit like simpler, is, okay, you've got diagrams, we don't really care anymore what an input and an output is. We can connect outputs to outputs, inputs to inputs, outputs in the future to inputs in the past, all okay. This is exactly the same thing. Just saying that is exactly the same thing. And this is, of course, a much simpler way to say it because there's no equations involved. It's actually just a liberal version of a diagram. It's a liberal version of a diagram. Okay, so how are the two connected? Well, you simply replace your triangle, your big triangle, with a cup-shaped wire, and that's it. And then these equations we had, they become just like Well, yeah, equations about wires, right? Now, if you think of these wires as electricity wires, it doesn't really matter whether you twist them or whether there's a bend or anything like that. Doesn't matter. So that's your equation. So actually, you don't have any equations. You don't have any equations. There's no equations. It's just the idea of saying you've got boxes and you've got wires and you can wire anything to anything. So that's very simple. That's basically realizing this idea, which was here articulated in these equations, but in a sort of way that there is no equations, just totally free. So that's nice. That's nice. So that's what we're going to work with now for the rest of the talk. This is the type of thing we like. Just for the, I think a lot of people have seen this, what I'm going to show now. Okay, but it's important to make a connection with the things I'm going to talk about in language and cognition. So okay, so this is something you all recognize as an example of how powerful this formalism is. This is cyclicity of the trace. This is not a theorem. This is not a theorem. This is not a proposition. This is tautology. Because you got a diagram with two boxes on the left, two boxes on the right, same boxes and same wiring. This is not an equation even. This is tautology. This is cyclicity of the trace in linear algebra. So it's not something you prove even. It's just there. Here is quantum teleportation. You just look at the wires on the left and you look at the wires on the right and what is connected to each other. It's all the same. It's all the same. I mean, you may be a bit confused that there is a box on the left which is rotated 180 degrees on the right. Well, it doesn't really matter, you know. I mean, it's in the same direction on the wire, and that turns out to be the transpose. If you look in linear algebra, what this means is just a transpose. So this 180-degree rotation. So this quantum teleportation, I'm not going to spend time explaining this because otherwise you don't have to buy our book anymore. But the main thing is that you have to look at the shape of the thing. Just look at the shape of the thing. Like you got like a bent wire which you then yank and you slide some things around, and that's the equation, and that's sort of the formalism. And if you read this is just one very baby example of diagrammatic reasoning in quantum mechanics, but for a few years now here in Oxford, I'm just giving all quantum foundations and quantum information using diagrams like this. You can give the entire theory. That's what we have. Like Robin took the course, and Robin also taught the course to students, so he knows it very well. But yeah, so you can give an entire course with these diagrams. That's not the subject of the talk today. Subject of the talk is that you look at this diagram, and then you look at something else, which is this diagram. I mean, at first it just looks like a more complicated version to the picture we had on the left, right? I mean, you still have, okay, here it was Alex and Bob, right? Here it's Alice and Bob. A slight difference of actors. I mean, I could have changed the names, so it doesn't really matter. But Alex actually likes me, so I couldn't make this sentence. So Alice does not like Bob. So what you see here is something which uses exactly, ignore the little pi symbol, just ignore it for now. What you see here is something which looks exactly the same as the quantum teleportation picture. You got a state here, which is this triangle. You got triangles here. You got these cups and these caps, which I discussed before. They are here. But then there is this mysterious thing that there are some words, dos and not, and stuff like that going on. And the reason is what you see here is just a sentence, a natural language sentence, and the bottom part in the dotted line is what represents meaning, and the top part is what represents grammar. So we use exactly the same formalism, and suddenly I claim to be talking about natural language and natural language meaning. And I mean, it's nothing new. It's nothing new. You all know this. You all know what's going on here. It's all in your brain already. It's there because this is the reason why there aren't any dictionaries for sentences. This picture. What this picture does is It takes the meanings of the word Alice, which you can look up in a dictionary, the word Bob, which you can look up in a dictionary, the word like, which you can look up in a dictionary, does and not. Somebody can explain what it means to you. And then you get a sentence, Alice does not like Bob. A sentence you probably never heard before until today. Am I right? Did anybody ever hear that sentence? Alice does not like Bob. I'm sure nobody of you has ever heard that sentence. Well, you hear it for the first time today, and you actually know what it means. You didn't have to look it up in a dictionary for sentences. You knew immediately what it means. And so how do you do that? Well, I mean, I claim this picture tells you how you do it. That's my claim. So essentially, what this picture is a computation of the meaning of a sentence given the meaning of the word made up from it, and using the grammatical structure to mediate the interaction of the word. That's what I claim this picture is. So I'll now explain how we get to this picture by saying something about what is grammatical structure and by saying something about what is meaning. Right. So I'm going to now like a little bit of historical digression of how people thought about grammatical structure. I mean, one person very much associated with this is Chomsky, of course, but the sort of more harder mathematical characterization was done by Lambek, who died a few years ago. So in the 1950s, he wrote a paper which was the mathematics of sentence structure. And it's not really important that you don't recognize or that you can't parse the mathematical symbols on these slides. It's not essential. So basically, we're dealing here with certain partial order structures, which also have a multiplication, and then there is some interaction going on. For those who know category theory, this is a monoidal closed category with non-symmetric, so with both left and right adjoints. And it doesn't matter, but anyway, that's a structure Lambek came up with in 1950s, and most linguists and all that have been using this since then. Like people who are interested in grammars of sentence and parsers, which in modern applications, people who try to figure out grammatical structures using symbolic methods, they use all this stuff. But then the same Lambek, the same person, in 2000 said, I'm going to change my grammatical gadget a bit. Still similar in spirit, partial order with some stuff. Looks a bit different. It's not important what you see there, but what is important is that it's the same as this. I mean, it may be hard to associate the two equations on the two things on the bottom there with this, but it is the same thing. I can guarantee you that. It's the same thing. What you see here is actually a more general version. What you see at the bottom is a partially ordered version, and stands to how a partial order stands to a general category in category theory. No, that doesn't matter, but the key thing is he came up with equations, or he defined grammatical structures actually by the sort of wires we saw before and the equations we saw before. There's one, and I mean, the way I learned about grammar was I was giving a talk at McGill in 2004, and I knew that Lambek had done all this grammatical stuff, but I never looked at it ever. Then I was talking about teleportation there, the stuff which I've heard show, and then Lambek said, hey, these are pre-groups. Pre-groups referring to his grammatical gadgets. Because he immediately recognized that they were the same thing. They were the same thing. So they're not exactly the same thing, in the sense that that a thing on the left and a thing on the right is not the same. It's important in which order your things come, because that happens to be important in language. So the order is important. That's the only difference, and that's why here there's a few more equations. But it doesn't matter. Let me explain what a pre-group is. The easiest way to explain to somebody who knows a bit physics what a pre-group is it's something that's almost a group, but the left and the right inverses are not equal. So you got a notion of left inverse and you get a notion of right inverse, and they don't coincide. And it's manifestly a non-abelian group, because order of words is important in language. So basically, how do you start? You start by picking out some things which you call basic types, in this case, basic grammatical types. And a basic grammatical type is, for example, a noun. Another basic grammatical type is a sentence. A sentence is a clear entity of grammatical structure. A noun is a clear entity of grammatical structure. And then there are things which are not basic grammatical type. One example is a transitive verb. So what is a transitive verb? A transitive verb wants to be a sentence, but in order to be a sentence, it needs, in English at least, a noun on the left and a noun on the right. Like Alice hates Bob. So the verb hates, wants something on the left and something on the right, being Alice and Bob. So how do you write this down? You write this down by what I've written down on this slide. You got this S in the middle, and then you got this N with a -1 on the left, meaning on my left I want the noun. So N minus 1 means I'm the inverse to a noun, so I want the noun to eliminate me. Same on the right. I want the noun on the right to eliminate me. And then you get something like this. So what the computation you see here is sticking a noun on the left and sticking a noun on the right of this transitive verb. They cancel out, and you end up with a sentence. And that computation shows you that the structure of a noun, a transitive verb, and a noun together make up a sentence. That's how these gadgets work, and they work for much more complicated stuff, and much more complicated grammatical sentences. But this is the essential idea, and you immediately see why this pre-group structure is so natural. You see it's sort of a very natural thing to have. The next idea is to actually do something different. Instead of writing this red line computation there, I'm going to represent my computation as a diagram. And that's actually, in this way, you're going to really see how this pre-group structure indeed corresponds to the ideas of these diagrams and these cups and caps. So what you see at the bottom there is noun, transitive verb, noun. And instead of what a mathematician does, like he scratches out n and n minus 1, we're going to put this cup-shaped wire to make them annihilate, like in Feynman diagrams almost. So they annihilate each other. And see, if we read this diagram from bottom to top, then you see we start with a noun, inverse noun, sentence, noun, inverse noun, and then these two, all this noun stuff annihilates each other, and only the sentence goes through. So we end up with sentence. So it's a diagrammatic representation of the thing. And the big idea, the only big idea we ever had was, okay, let's not think of this just as a computation and types, which is what these grammatical type calculi are about, but let's actually replace these types with actual words and meanings. And think of this diagram as an actual map or something like that, just like the wires in the teleportation diagram, which are linear maps. Just we can think in a similar way about this computation as a map and about these types as words. So what we see here now is we got the word Alice, which has a meaning, a state, which you can model, say, in a vector space as a vector. You got hates, which you can model by a vector. You got Bob, which you can model by a vector. And then you got this thing coming out. Well, I mean, people who know quantum mechanics and have worked computed teleportation, they know exactly what this map looks like. It's actually the inner product. It's like taking the inner product of two things, this cap structure. And then an identity comes through, so you can compute this thing, and you get a vector which is supposed to represent the meaning of the sentence. So this is supposed to do what we do in our head, and now we compute meanings of sentences. That's sort of the claim. Okay, that's nice. So effectively, a slide. So why is this important? Why is this important? This is of course important because natural language processing using Google and all that, doing automatic translation is big business these days. So one reason people would care about this is that Google doesn't really understand grammatical structure when you type it in a Google search. And this is actually a theory which gives grammatical structures to language a meaning. Because something like this didn't exist before we did it. The only thing which existed was something called Montague semantic, but this was entirely truth-based, which allowed you that if you know one sentence is true, to derive that another sentence is true, and stuff like that. So, but that was but like dealing with meanings of complicated structures like vectors and stuff like that didn't really exist. So okay, so we came up with now an algorithm to compute the meaning of sentences giving the word. So you basically do the computation, the type reduction, then you treat it as a linear map and you apply it like the vectors. That's what I just said. So here is an algorithm for vector meaning composition. Okay, good. We did experiments and stuff like that, and we outperformed everything else. Not surprising, because there was nothing else. But people did just weird things. Like, I mean, they take the vectors of words and add them up, and that's the meaning of the sentence. Or they do something else just randomly. They convolute them. Okay, that's the meaning of it. Clearly, this is not going to work because there's no grammatical structure. So it was very easy to outperform. But anyway, so we got famous, a lot of attention, blah, blah, blah. That's good. I became deemed the crackpot, quantum linguist. I mean, how more crackpot can you be? Okay, that's good. Okay, but there's some really, so let's forget about the practice and the contemporary applications of these sort of things in natural language processing. There's a lot more going on here, because the picture I showed you, there are these words does and not. And these words does and not are not vectors. Of course they're not vectors. You're not going to empirically or whatever figure out what the meaning is. They actually, if you reverse engineer this picture and you follow the wires, so you start with Alice, you follow the wire, you end up in like. You start with Bob, you follow the wire, you end up in like. Then you start in the middle of like, you follow the wire, you go to the circle with pi, you follow, and you get out. So basically what is there is Alice, Bob, like, not. This is kind of what it's supposed to be. So why is this? Because we reverse engineered what does and not should be, given the grammatical structure, which we got in a text, in a book from Lambek, which is stuff you put on top. What you put on top is grammatical structure. You get it from a book. If you're smart, you take this from a book. You put the top wiring, and then we reverse engineers what does and not should be in order to make this work. That's nice. So you can actually come up with sort of logical interaction structures for these words like does and not. And here is another example. I mean, you see something we haven't seen here, like the dot there. You see under who, you see a dot above who. So that's a relative pronoun. So we actually have to throw in some extra structure, which is not just cups and caps, to capture relative pronouns. But so now we have she who hates Bob. That's a very different type of structure. Very different type of structures. I mean, I could explain, but I don't have the time, why this is supernatural to have this structure. But I mean, where did we get this structure? Well, if you read our book, you'll find something which is called spiders there, which are things we introduced to model classicality. We wanted to model classicality in teleportation because teleportation involves a phone call from Alice to Bob, and we needed to model that. And obviously classicality is different than quantum, and basically these spiders are classical things, and the fact that you got more wires coming together mimics the ability of classical systems to be cloned. And then you can prove a theorem that, so basically here, this is the only equation governing these spiders. If you got two spiders, they fuse together, and this is a bit like, I mean, if you can make copies as much as you want, and it doesn't matter which thing you copy further to get more copies, you know, because they're all copies. So that's a little bit what this equation articulates, and you can actually prove that any type of linear maps obeying this sort of equation correspond to some orthonormal basis in this way. They're just this sort of thing. You make a sum of a bunch of cats and bras of basis vectors, and you get such a spider. And they're the unique things which behave like that. I mean, I'll scan over this so you can do teleportation with a classical. People who know teleportation, they'll see now here you got teleportation with a telephone wire, which is nice. Not so important. We got these logical meanings here, and the sort of thing you can do now is you can stick some vectors in. I've got density matrices here, and then you can do some sort of nice toy computations. You can say she who hates Bob you compute what she is, you model what she is. She's a woman, so it's any kind of woman. Then hates is the combination of things which hate something else. Bob is Bob. And if you stick all that together in this diagram with the spiders, as I explained before, then you get out Alice. Actually, you get out a lot more people because everybody hates Bob. But it doesn't matter. I mean, I tried to be nice to myself and only made one person. Right? Okay, so that's what this computation does. This grammatical structure, and I gave some idea how we think about grammatical structure. But I think, okay, now comes a big claim. I don't think grammatical structure is anything that has to do with human thinking or human creativity or social culture or anything like that. I think grammatical structure is about things like an action which needs two participants. For example, I think, in my opinion, a lion totally understands the grammar of a transitive verb sentence with two nouns. Totally. Because a lion perfectly understands the hunting process, perfectly understands that there is an object and a subject there, and that you can't swap these things, that they have very clear roles. One role is for the one eating the other thing, and the other role is for the other thing trying to run away and not being eaten, and hopefully failing to do that. So that's grammatical structure of a transitive verb two noun thing. That's how I think about this. So it's an action which needs two participants. I mean, I've explained the example of the line. And if you are more liberal like that about grammatical structure, you can just take this structure, go away from meaning, apply it to, or go away from sentence meaning, and maybe translate it to meaning of concepts, or the way we conceive things, or any kind of conception of humans, or human interaction, or animal thinking. Why not? So we tried to do that. I mean, we didn't know anything about cognition, so we looked for one of the most famous people in the world in this area, which is a guy called Peter Gardenfors. And he wrote some books on things which are called conceptual spaces and meaning spaces. And we made it compositional, because these things couldn't be composed. So what are these things? I mean, I'm really underrepresenting the person in what I'm going to do to make it easy and straightforward. But so, like, he likes to think of concepts as convex structures, like you see some examples here, convex structures like this RGB color cube. Actually, he doesn't use the RGB color cube. He uses like the disk, the color disk, with them white on top and black on the bottom. But it's just too difficult to draw for us. So we took just this color cube. And then, and the same, you got like the taste tetrahedron. That's wrong too, because there should be 5 corners, but we can't draw that neither. So it doesn't matter. It's not important. And then, what is a color? A color is actually a subset of that convex region. Like we drew yellow there, and we drew green. And this, I mean, the choice of these subsets is totally cultural. For example, the Greeks didn't have blue. Like everything blue they called green. They didn't have a concept of blue. They just thought it's part of green. I mean, they obviously they saw that blue looked different than green, but it was another shade of green for them. So these colors are very cultural. And so obviously, what are the two ingredients here? The two ingredients in forming concept like that is like taking our senses seriously. So if we want to think that this is the way we think, it's like taking our senses very seriously, and also identifying that there are cultural conventions and cultural habits which we have, and having an interaction of the culture and sort of the senses. Anyway, so that's the sort of thing it does. And okay, so we want to reason with these things. So basically what we need to do is like come up with an interpretation of our boxes and wires where these things make sense. It's a bit different than vector spaces and all that. I mean, I'm not gonna. We found something which is called a convex algebra, which is due to a person called Bart Jacobs. It doesn't matter what it is, but it's like one of these. I'm gonna just skip this to not confuse you. But the essence is like you can really take the Cartesian product of these convex things, and build bigger concepts out of smaller ones. You got a notion of cups and caps, which are exactly the same as you would find if you're playing with relations. So it's quite easy to work with. I don't have time to explain the formal thing, but now we can sort of start. I mean, these are all toy examples to say what a banana is. A banana is a green thing, which is kind of Swedish, but maybe a bit bitter. And then the last thing is about texture, and it has a certain texture. You may like the texture or not. It's banana texture, right? And then an apple has a different color and different taste and different texture, and beer. I mean, I like that one. I mean, yeah, there you go. Actually, I mean, this picture of beer was drawn by an English person because I love my beer Saar as a Belgian. Like we've got the super Saar beer, which is excluded here. And we actually have very sweet beer, which I don't like, but it's there too. We don't have salt beer. So at least that bit is right. Right. And then you can do things like, okay, my diagrams are upside down here because they're again drawn by an English person. I don't know why. Anyway, they always go in the opposite direction, you know. So what you see here is like a phrase of an adjective with a noun, yellow banana. And then basically what you get is, I mean, if you compute what all this stuff does, then you basically kind of get the intersection of the regions of yellow and banana in the space of stuff. The space of stuff, which is these composite systems, right? And then, so you get an intersection of something which is yellow and which is a banana, which is a yellow banana. Right, there you go. And then here is another example. Fruit which tastes bitter. Fruit which tastes bitter. You can think of this as the intersection of fruit and something that tastes bitter. And that happens to be a green banana. Yeah. You compute this and you get a green banana. I mean, there's probably other fruit which tastes bitter, but I mean, at least a green. But in our little toy example, that was a green banana. So you compute this and you get. So I mean, it's nice. So we're doing some calculations with things which are a bit closer to concepts we thought. And this is this guy Gardenfors, and he read our paper, and he was happy. He liked it a lot. And then he criticized one thing in particular, and that was the separation of grammar and meaning. Because these things are a lot more intertwined, and even in language they're slightly intertwined. But I think when you go to Gnishin, they're much more intertwined. For example, in sentences, you got ambiguous grammar, which depends on meaning. Sometimes grammar is ambition, and you really have to know the meaning of the word. And sometimes even that's not enough. You got like these sentences which can totally mean two things, and you need some other sentences around it to know what they really mean. Then there is this other funny thing in English that we have a special order on adjectives. For example, we say large red. Well, we not say large red. We say red. No, yeah, we say large red with car, but we don't say red large car. There's clearly something about the structure of language which takes into account these things. And then, even more striking, if you go to prepositions like on and next to and after, they have clear spatial connotations already. So the grammatical role of prepositions seems to assume some spatial connotation. So, okay? So what we want to do now, and I'm going to soon end here, is, I mean, this is something we're working on now, is instead of working with these convex spaces, really trying to represent spatial meanings of things. So here is an example of these propositions. We want to sort of be able to put a pen on the table. So you got the concept of pen, you got table, and proposition on actually places the pen on the table. That's the idea. Right. I mean, the way I think about it is actually that you want to produce movie clips. That your nouns are actors, like cowboy or an Indian. Your verbs are actions between shooting, and your sentence is the movie clip where the cowboy shoots the Indian. So that's what we want to do. We want to take one of our diagrams and then produce a movie out of it. It's sticking in like images. I mean, it's quite realistic, you know, because if you type in a word well, let me say, we actually want to do better. We want to do that. We want to actually say a sentence, and then the sentence gets translated to the pictures, and so then you get the movie. So you say a sentence in natural language, and that gets translated to a movie clip. right? And it's not so difficult because Google already does that. If you type in a word, you get the image. It gives you an image. So then there's not too much obstacle, and we know the structure of the interaction, so we pretty much got everything. Huh? I mean, but this is like a master student project, I think, nothing more. Okay, let's go more interesting. Is that what we do when we are talked to? So if somebody tells you a sentence, if somebody tells me a sentence, I don't see the words in my head. What I see in the head is a movie of what they're talking about. So basically, this mapping of the sentence diagrams with sentence meaning on the movie clips with movie meanings may be exactly the process what we do in our head when we perceive things. Translating sentences into movies. I mean, probably it's a combination of more things, but clearly this gives. So there's clearly a very. I mean, I know people doing a lot of experiments on how students perceive mathematics, whether they perceive it symbolically or whether they perceive it graphically, and the bias seems to go to the graphical representation are much more helpful than the symbolic representation because they're probably much closer to our thinking. So this sort of model could help there, and yeah, so that's what I'm saying here. So that's wait. Yes, okay. So the opposite, of course, that you visually perceive things and that you want to put it into language. That's the other process. But I think the more interesting side of turning movies into language is that it may actually be the origin of grammar. That the lion sees the movies in the head or imagines the movies. And then they evolved, and then suddenly the movies we saw in our head actually became grammatical structure. I mean, I know Chomsky is just going to kill me, but when he hears this, because he always thought as grammar as something very human given, but I can perfectly see, like, from the hunting line, whatever it's imagining evolve in the structure of a transitive verb sentence as we speak. I don't know. It's exactly the same structure. That's all I know. Okay, I think I can end here. Not going to say much more. Just want to show you the picture of my daughter, and then say, and since I talked a bit about education, this summer we're going to go to schools and we're going to show that kids teach learning diagrams can outperform Oxford students, like show a few twats here, Oxford twat students in doing quantum physics. And that's another case. I mean, this is, one can say this is justification, but it's another case to make that we actually think much more diagrammatical than we think symbolic. So, but we're going to effectively do these experiments. We started to set everything up, and we're going to show that diagrams. So, I mean, so in my talk, diagrams came in a lot of layers. It was the language of quantum mechanics, it was the bridge between quantum mechanics, language, and cognition. But in the end, it's maybe also the way we actually think itself. Yeah, I end here.